Hello everyone. In this video, we are going to talk about LU factorization, or some people call it LU decomposition. So what is the problem statement? The problem statement is if I have a matrix A, and this matrix A is an n by n matrix, decompose it into a product of a lower triangular matrix L and an upper triangular matrix U. So before I move on, two questions. One, is this only for square matrices? The answer is yes. If a matrix A that we are working on is not a square like m by n, the factorization that we use is called QR factorization, and I'm gonna talk about that in one of my future videos. Okay, so right now, yes, we only really work with square matrices. That's one. Two, can I always do that? Can I always write A as a product of a lower and an upper triangular matrix? The answer is yes, if we do sometimes we need to do something called pivoting, and I'm gonna show you that. Okay, so we need the permutation matrix, and in that case, instead of writing A as L times U, then we write this permutation matrix P times A equals L times U. Okay, so if we do the permutation and do the pivoting, then yes, this decomposition always exists. Okay, so these are first two questions. Now, you might say, why should I do that? What's the point? Why should I write a matrix like the product of two lower and upper triangular? One of the main applications is to solve a linear set of equations. So if A is my coefficient matrix times X, which is the unknown vector, equals some right-hand side vector, which is known, and I need to solve that, one of the methods for solution, which is not an iterative and a direct method of solving, is to do it with LU factorization. What does that mean? So here you write this A as L times U, so it's going to be L times U times X equals B. And now you're going to call this U times X, you're going to give this guy a name. You call it, for instance, a vector Y. So now your equation is L times Y equal B. And we know that if we have a system of equation where the coefficient matrix is only a lower triangular matrix, I can basically solve for the first variable and then start substituting all the way down and find all of the values in Y. And that's what you do in Gaussian elimination, right? The goal in Gaussian elimination is to convert your A matrix into a lower or upper triangular matrix. So once I have this, then the substitution is going to easily give me all of the Y values. Now, if I have the Y values, I'm going to plug them back up here. And now my equation is U times X equals Y. And again, since Y is known and U is known, this is again, the coefficient matrix is an upper triangular matrix. This time you start with the last variable and substitute all the way upward and you solve for X. So again, this guy works with substitution, and that will give you the unknown X vector. Okay, so you see that it can help you solve a linear set of equations very efficiently if you can break A into L times U. So first you do the forward substitution, which is this part, and you find Y, and then you plug Y into U times X and find X, and that is called backward substitution. Okay, and not only it's good when this B is only a vector, if this B is a matrix, which we call a system with multiple right-hand side, that will also work. What does that mean? So in this case, instead of your unknown X be a vector and right-hand side be a vector, X and B are both matrices. Okay, for instance, what does that mean? Let's say A is like 1, 2, 3, and 4, and B is like 5, 6, 7, and 8. So what does that mean? Means one time A times first column of X equals first column of B, which is 5 and 6, and then A times second column of X equals second column of B, which is 7 and 8. So once you have x1 and x2, then your x, the solution, is going to be column x1 and then column x2, okay? So in this case, your x is also going to be a 2 by 2 and your b is a 2 by 2. So this is what we call a multiple right-hand side system, okay? Your right-hand side has two sets of values in it, and so your x will have two sets of solutions, okay? And the good thing is the same L and U could be used in all of them, because this A can be replaced by L and U, and this A can also be replaced by the same L and U. So if you do that LU decomposition for that A one time, all you need is just look at the right-hand side and just do the forward and backward substitution with a different right-hand side, but the same L and U. So it is extremely efficient when we say we have systems with multiple right-hand sides. Okay, so that's one of the motivations for LU factorization. But is that the only reason? No. Let me give you another motivation. So you know that one of the things that you need to do with matrices is to calculate their determinant. So if you can break down A as L times U, you know determinant of L times U can be written as determinant L times U and determinant U. And when a matrix is upper or lower triangular, the determinant of it is simply the product of the diagonal element. So it's going to be the product of diagonal elements of L and diagonal elements of U, and you can even multiply them together, and that is going to be the product of them, correct? So if, for instance, I say, hey, what's the determinant of this matrix? That's very easy. That's just 1 times 1 times 1. What is the determinant of this guy? That's 1 times negative 1 times 2. Okay, so upper, lower, and diagonal matrices, they all have their determinant is the product of their diagonals. Okay, so if you have L and U, determinant of A is going to be extremely easy to calculate. Now, question is, how do you find L and U? Well, if it's in MATLAB, it's not really a hard thing. In MATLAB, all you need to do is to pass it to the command LU, and it gives you L and U. Yeah, very easy, huh? Yeah, but how does it do it behind the scenes? So let's talk a little bit about it, and then we have to come and talk about the pivoting and another reason that this LU factorization is something important and something that we need to learn. So first, let's learn how we can do LU factorization. So the operation for that is basically Gaussian elimination, which is extremely easy. So let's say the matrix A that they give you is like this, okay? And here it doesn't need to be 3 by 3, it's just as a sample. So let's say this is your A matrix, okay? And you have to break it down as L times U. So how would you do it? You basically do the Gaussian elimination. If you remember, in Gaussian elimination, you find the ratio of A21 over A11 and then the ratio of A31 over A11. So you multiply the first row, if you call this row 1 and this is row 2 and this is row 3, then to convert these two numbers to 0, right? We want to convert A basically into an upper diagonal matrix. Then you multiply row R1 by this ratio, which here I call it M21, right? And then I multiply row 1 by ratio M31 and basically subtract them from row 2 and row 3. And if I do that, I will get these two numbers into 0. Yes. So if I do that, so my first row operation is going to be row 3 minus M31 times row 1. And then row M2 minus M21 row 1. If I do that, it's going to be A11, A12, A13, 2 zeros, and then some new numbers. I can call them A prime 22 and 23 and A prime 32 and 33. Okay, they are not going to be the same number. Now that I have these, to get rid of this last number and convert it to 0 so I get a fully upper triangular, I need to find the ratio of this A prime 32 to that A prime 22, and I can call it, as you can see here, I can call it, for instance, M 32 right here. And then if I do that, now my last operation is going to be basically row 3 minus M32 times row 2. And then I am going to get this. And I call this a double prime 33. Again, that means it's not the same number. And now you see this is an upper triangular matrix. Good. So first of all, the U that you want is this ultimately U that you found. This is the U. This U that you found by row operation. This is the U of LU factorization. There we go. So this is your U. Now what about L? For L, it is going to be a lower diagonal matrix, and the diagonals of that in this case are going to be 1, 1, 1. So your L matrix is going to be 1, 1, 1, and then 0, 0, 0. And your numbers that you found, M21, M31, and 23, they are going to sit here. So this is going to be M21. This is going to be M31. This is going to be M32. Those ratios that you found for the pivots, those ratios are going to sit into L. And now you know that if you multiply L by U, you should get your A back. And that is basically the essence of LU factorization. Okay, so it's very clear and very deterministic. So now, let's go ahead and do one example, and then we come and look at the case stat. What happens if one of these numbers that you're dividing by, one of these pivot numbers, is 0? Because you cannot divide by 0, okay? Those ratios become infinity. So first, let's look at the case assuming that these A's, these diagonal ones, pivot ones, are non-zero. So here is an example. This is the matrix that I have. A or A prime, doesn't matter, it's just a matrix. And if you don't like it, we just call it A. So this is my matrix A, and I want to write it as L times U. So the first thing I do, I want to convert these two numbers to 0. How do I do that? I divide this number by that, and I divide this number by that, and I get my two ratios. So M21 is 1 over 1, which is 1. M31 is 2 over 1, which is 2. So far, my L matrix is going to be 1, 1, 0, 1, 1, 1, 0, 0. My M21 is 1. My M31 is 2. Okay, so already I found most of the L. And then what? Then, of course, I multiply row number 1 by this number, subtract it from row 2, multiply row 1 by this number, subtract it from row 3. If I do that, my last two rows are this. So at this point, your A matrix is turned into 1, 2, 1, and then 0, negative 1, negative 1, and 0, negative 3, and negative 1. Now you're almost there. The last thing I need to do is to get rid of this one. So you have to convert this to a 0, and you're good to go. For that, you need to divide this number by this one. And that's exactly what you do here. You get this ratio, which is 3. So that 3 is going to sit right here. And there we go. My L matrix is done. So now I multiply row 2 by 3, add it to, or subtract it from row 3. And if you do that, then your last row becomes this. So now at the last stage, your A matrix becomes this one. You see clearly this is an upper triangular matrix, so that is your U, as I said. There we go. This is your U. And as I said, your L is this one here. Done. Okay, so that is your L, this is your U, and you can always check that, right? You can always go ahead and check that and see if that's correct or not. So here, to show you that, let's do a CLC clear. So I define my A. Let's see if my A is this matrix here, right? So it is 1, 2, 1, 1, 1, 0, and 2, 1, 1. Yes, it is exactly that. And so here, my L, let me go with what we found here, correct? So I'm gonna type it in. Good. So that is your L I type. This is your U, okay? And now if I say L times U, look, this is it, and this is your A. I need to redefine A. There we go, right? And let me do L times U again. Look, you see? They're exactly the same thing. So you see, it absolutely worked, right? So this is how you do LU factorization. Now, before we talk about what happens if one of those numbers in the denominator is 0, let's go ahead and look at the command that I told you to use in MATLAB, which is the command LU. If I ask MATLAB to do LU of A, would it give me the same L and U that we just found here? Let's take a look. That would be interesting, huh? So here, this B part of it, for now, we don't care about it. All we want is this L times U. So let me do something. Let me bring this guy up here and put something there. So take a look here. You see that definitely this L is not the L that I found. Okay, it's definitely not that one. Okay, it's absolutely not that. And of course, the U will be different too. And even worse than that, although U is upper triangular, L is not lower triangular, right? I mean, these two zeros should be up there, right? And it seems like if you move the rows of L up and down, yes, you might be able to convert it to a lower diagonal. So you need to take this first, basically last row and first row, you have to swap them. Then these two zeros will sit there, and then you have the 0 here, which again should not be, and then you have to swap the second row and third row. So really, this guy here, this row 2, should sit at row 3. Row 1 should sit at row 2, and row 3 should sit at row 1. Then yes, it will be a lower diagonal. And you might say, what is that? Well, if you look at MATLAB help, it says that if you just use it the way that I showed you, it converted into an upper triangular U, but a permuted lower triangular matrix L. Okay, so this is something that you have to be very, very careful about. That yes, it might be converted to a lower diagonal, but definitely is permuted. So that's the first thing I put here. Okay. And then you might say, well, so can I think that this guy is ever gonna give me some right answer, right? Well, the L is actually a lower triangular matrix. Yes. That is when you use the second format of it, LU and P equals LU of A. In that case, A can be written as P transform times L times U, or it can say P times A equals L times U. Okay? So if you use the form that it gives you a permuted version, this one, the second version, then yes. In that case, as I said, P times A equals L times U, or A equals P transpose times L times U. Okay? So now, and in that case, L is actually, in this case, L here is an actual lower triangular matrix. It's not going to be permuted lower triangular anymore. Now, when is it that we need to do it this way? Okay? First of all, so that the L that we get is really a lower. Second of all, as I said, when you do these divisions here, if these numbers, which we call pivots, if any of them goes to 0, you cannot divide by 0. In that case, you need to do a pivoting and basically swap some rows or columns or both to make sure those numbers you are dividing by do not become 0. Okay, let me show you an example of that. And we're going to see this case here. And we're going to see how to use it to solve a linear set of equations. And then I'm going to tell you another advantage of LU factorization as the last remark. So let's see how we do it. So let's say this is my A matrix in this case. Well, I need to convert these two numbers into 0, right? But for that, I need to divide these numbers by 0 in this case. That's my pivot, is 0. That is not going to work. So what do? I swap row 1 with row 0, and row 0 here, actually, if you don't like this, I call it row 2 with row 1. Okay, yeah, that might be a little bit confusing. So I swap row 2 with row 1. In that case, right, I take this and I take that and I swap them. If I do that, my permuted version of A is going to be this guy, correct? Now, for me to go from this A to this version of A, I need to pre-multiply it by a matrix that does a swap of row 1 and row 2. That is what we call a permutation matrix. So what is a permutation matrix in this case? Look at the shape of it. So if you look, the last row is just like an identity matrix, but the first row and second row, instead of this 1 sitting here, 1 sitting here, and 0 and 0, you see the 1 and 0 in the first and the second row are swapped compared to an identity matrix. Because you know, if you multiply any matrix by an identity, nothing is going to happen. So in this case, last row is the same. But if you look at the first and second row, you see that the zeros and the ones are swapped. That is the same as swapping row 1 and row 2 together. For instance, if you wanted to swap row 1 and 3, what would you do? In that case, row 2 is not going to be any different, but the numbers in row 1 and 3, these numbers should be swapped. So you get a 0, 0, 1, and here you're going to get a 1, 0, 0. This one will swap row 1 and 3. Yes? And you can imagine similar thing for 2 and 3. Okay, so in this case, P times A is this, and now can I use it? Yes. This one is already 0, so this is good to go. So here I just need to divide this 2 by 1 and get rid of this, so that becomes a 0. If I multiply first row by 2, subtract it from this, this guy goes to a -1 and this guy stays at 0. And now I need to make finally this one go to 0, and for that I need to divide this -1 by 2, which is -1/2, multiplied by second row, subtracted from third row, and now your A is going to go to a full upper diagonal matrix U. So you see here, I do need to do this, what we call pivoting or swapping rows, to avoid division by 0. Good. Now in MATLAB, if you want to get the LU and the permutation matrix, the command is LU and P equals LU of A. In that case, as I said, either PA equals LU or A equals P transpose L times U. Both of them are good. Now, in this case, if I want to use this version to solve my equation A times X equal B, so I'm going to replace that A. So it is going to be P transpose, actually, that is the transpose, P transpose times L times U times X equals B. And again, I call this guy Y. So you see that P transpose times L times Y equals B. And B is known, L is known, P is known. Can I solve for Y? Yes. So first thing I need, I multiply both sides of it by P, and it will be PP transpose times L times Y equals P times B. And the question is, what is P times P transpose? And the answer is, this is an identity matrix. Because what P does, if you look at it, is, for instance, this one. This one swaps row 1 and 3. Yeah, this is your P. Now, what is P transpose? Let me write P transpose for you. This matrix is symmetric, so P transpose is going to be the same as P in this case. And if I multiply them together, you clearly can see, let's look at just the 1, 1 element. So it's going to be first row times first column, and you see it's 1. Then first row times second column and third column, they are 0, right? So, and then second row times all of that, you're going to get the 0, 1, 0. And then third row, if you do it, you're going to get the 0, 0, 1, which you see is identity matrix. And that's always true because a permutation matrix, if P swaps 1 and 3, P transpose can swap 3 and 1. So when you multiply them together, it's like they are canceling each other. So they don't do anything. So there we go. You have L times Y equals P times B. And here I can easily use a substitution, forward substitution, to solve for Y. Right? Because I'm solving basically this. And once I have Y, now this is equals to U times X. And now I use backward substitution and solve for X, which is exactly what you can see here. Okay, and I can use backslash operator to do those forward and backward substitutions for me, which is exactly what Gaussian elimination does. That is backward slash in MATLAB instead of using inverse. So now you can clearly see how we use this. Now, two last things. One, let me show you that in MATLAB first. So here I'm gonna apply to that same A matrix that I had. I'm gonna apply this version that has P in it. Okay, so by the way, you might say with that permuted L and U, can you use backslash operator to solve for a system of equations like AX equal B? If you do that, would you get correct answer? So first, let me do this for you. So look at the answer. The answer is 2, 1, and 0. And clearly, if you multiply A by X, look, that is exactly the same as B. Do you see that? So definitely, even if it gives you this permuted L, permuted lower triangular matrix, still you can use it to solve your basically problem. No worries. But if your matrix is such that it needs permutation, the other version that has an extra P can do the job. Let me show you that one. Okay, so here I added this with permutation matrix for you, right? This is that secondary case, and I get L, U, and P, and I can show all of them, and I'm gonna show you the final solution X. So let me run this portion of the code for you. Okay, and this is that portion of the code. So this is your L. Now look this time. If you look at your L, this is clearly a lower diagonal matrix, and this is definitely is upper diagonal. And you clearly see from the permutation that if you see row 1 is swapped with row 3, row 1 and 2 are swapped, and row 2 and 3 are swapped. So all 3 rows are swapped, and this is the solution X. And now again, if I say A times X, you can see that is the same as B. Okay, I'm using the same B for both cases. Okay, yes? So you see that in this case, I divide L backslash by P times B instead of just B. And the second part, the back substitution, is the same. So this is what this is, LU factorization. Now, let me tell you a couple of interesting things before we finish this video. One, is LU gonna return the same answer every time? Well, not necessarily. The answer to LU factorization is not unique if some condition are not satisfied. Like what? Like remember here, when we did the L, we made some assumption. The assumption was that the diagonals of R are all 1. If we don't enforce that, so diagonals of L could be any number other than 1, then the numbers in U will change accordingly and you would get different answers. Okay, so that is one of the cases that you have to make sure it happens. Now you saw that in MATLAB, if you use the version with P, then L was actually with 1s in the diagonal, right? You can see that here, here, and here. Okay, but the original version that was like this, first of all, L did not have the 1s in diagonal, and second of all, it was clearly permutated. So that's one. So, and then of course, different pivoting strategies can lead to different P, L, and U, like partial, complete, or no pivoting, and if your matrix has some specific structures. But if everything is the same, so you are forcing L to have 1 on the diagonal, you're, let's say, using partial pivoting, then yes, ideally you should get the same answer. Now, by the way, since I talked about determinant, let me show you one case here. So if I show you, in this case, the determinant of A, look at it, it's -3, right? And let's look at the determinant of L. L is determinant 1, P is determinant -3, and U, sorry, and P has a determinant of 1. So you see, if I multiply determinant of L by determinant of U, correct, times P, because it's PLU, right? You see it's also -3, which is the same as A, and of course it should be. And I could just multiply those diagonal elements. Now, one last thing before we finish this, and that is about the stability. So if we use the partial pivoting that MATLAB is using, and it showed you, this method is numerically more stable for solving this system of equation AX equal B than some simpler methods like Gauss-Jordan elimination or Gaussian elimination. Why? Because as you know, in Gauss-Jordan elimination, you turn this A matrix into an identity matrix at the end of the day. So not only you convert it to a upper diagonal, but then you convert it also to identity. So that means you do some extra operation here. And the more operations you use because of round of errors, your error can grow and your numbers can be off from your actual solution. And so this is what we call the growth factor. And so in general, you can show that because this LU factorization takes fewer operations and arithmetics, it is more stable, especially when the numbers in A are quite a bit different scales. So you have some very, very big numbers and a bunch of small numbers. That's where this method is, in terms of final solution, is more stable than a method like Gauss-Jordan elimination. So it is really something important in numerical analysis and linear algebra, and it has a lot of applications. Hopefully you learned something in this video. I'll see you in the next lecture. Thank you.